despite years of research, more people die from heart disease than any of the combined deaths for cancer. And so, fortunately, we live in a time when data science is being used to help us model heart disease and to be able to predict and to prevent, and it is saving lives. And in this video, we are going to learn how to perform those very same machine learning type activity. My name is Dr. Yuwona Thiessen, and this is a new machine learning series conducted by Simplilearn. And if you want to be notified when we upload other videos, please like and subscribe. All right, so machine learning and cardiovascular disease. Now, cardiovascular disease or heart disease is very common, and so there have been several projects that whether from private organizations or the government, where data has been collected. There's lots and lots of data, health data on thousands, maybe even millions of patients, and we can use said data to model heart disease. So for the video project, what we're going to do, we're going to combine some slides to explain the concepts, and then we're actually going to go to the Jupyter Notebook, where we will use Python programming to perform these data science, data analysis activities. We will do all of the steps, and eventually we will get to building a few models, including a decision tree and a logistic regression, and maybe even a support vector machine. But we're going to take each step, and it's going to be divided in sections, so that way you can come back to the sections that you may want to review. So here I have my lovely acronym that is supposed to help you remember the steps involved in machine learning. In any machine learning project, you need to have an acquisition of data. So acquire, you need to filter said data, then you transform the data, and you explore the data. This is where you get an understanding of your data, and finally you're going to split the data. There's going to be two sets of splitting, and then the data will be ready to be put into the algorithms for modeling. So the first step is the data acquisition. Of course, you can't do data science without data. So you need data, but you don't just need any data. You need quality data, and you need data that is specific to the project, the phenomenon, the question, the business problem at hand. And so there are several ways that you can obtain that data, but it is important that the data is accurate, that it is quality data, because the quality of your model will be a reflection of the quality of your data. So you can scrape it, you can extract it, you can query it, you can collect it, however you get it. You just want to make sure that the data that you get is the data that you need for your project. So once you have acquired your data, then you're going to filter your data, because data always comes messy. It's from real people in real lives, and so there's always going to be some outliers. There'll be noise, there'll be errors, there'll be duplications, there'll be missing numbers, missing values. All of this you have to look for in your data set before you start doing any kind of data analysis, and you want to get rid of those issues, because you want to make sure that your data is clean, that it is organized, and that it is accurate. So those are the things that you're doing as you process the data. So after you have filtered your data, now this is where you're going to do the transformation, right? And so you are going to either be transforming the date from text to a Python or a Pandas date time, or you may be transforming text values into numbers and integers, because that's what you will need for the algorithm. So you may need to create some dummy variables as such, or you may just need to be transforming some values, continuous values, to a log because it's not normally distributed. So these are the things there. It's a host of transformations that you can perform on your data set, but you have to know what is in the data and what it is you're going to require of said data, and that's where these transformation steps come in. Sometimes there are missing values that you need to impute, but you will have to look at the data. Now there's some basic steps that you take, and there's when we do the programming, you'll see how we can identify some of these issues and rectify them. So once we have transformed the data in terms of making sure that the format is appropriate for our data science activities, then we do the exploration. And this is my favorite part. I love data exploration. This is where you got to get your hands dirty and get an understanding of the data. And this is where all of the data insight comes from, right? This is where you find out what are the trends and the patterns and the anomalies that are in the data. This is the insight that informs the data decision making, as it were. And so you want to make sure you have a very good understanding of your data. You're not necessarily going to be sharing all of this with the shareholders. This is for you so that you can be better at your data science machine learning activity, right? So you want to find out where the correlations are. You want to develop and test some hypotheses, and of course you want to generate some visualizations. The visualizations are extremely important. When we start doing the coding, I'll show you how when you visualize your data, there are things that you can see only when you generate a chart or a graph, right? So looking at raw numbers in a table, you will miss quite a bit if you don't create some charts and graphs. So once we have a good understanding of our data, and so we think that we are ready. So sometimes with the exploration, you may need to go back to the transformation, or maybe even back to the filtering stage. There is some type of a cyclic process here with these three. But finally, when you do get to the stage of modeling the data, this is where we do the splitting. And there are two splits. You split X's from the Y's, or the variables or the predictors from the target. And then the second split is where you split it into a train and test. And then you're going to use the train to model the data, and then use the test to evaluate the performance of your model. So let's get to some coding now. So I like to think of machine learning as a process like baking a cake or making a pie or making pizza or something. So the first stage, of course, is always assembling all of the ingredients and then all of the utensils that you would need. And then the second stage is doing the filtering of the ingredients, so you're getting all the lumps and everything, the flour is fine and you have everything, it's accurate and it's organized. And then you're transforming some of the ingredients. So for example, like when you have to melt the butter, you're transforming it from a solid to a liquid. Similarly, you may need to transform your data from text to integers. And then once you have all of that, now you're going to mix everything together. You're going to get your hands dirty, and that's where the data exploration comes in. And finally, when the flour is all needed, now you're going to divide it into the individual, balls or rolls or pies or whatever, and that's what I like to think of as the that splitting into X and Y, and then train and test. So let's gather all our ingredients together, and this is where we're going to move into our notebook. And I have decided that I'm going to use the Google Colab for a number of reasons, but you can do this, in your own Jupyter notebook directly on your system, or you can do it through Anaconda, whichever way you choose. But Google Colab, it's free, and I'll put a link to this actual notebook in the comment sections to this video. All right, so this is my Jupyter notebook in Google Colab, and here you see I have the first step. I'm importing the modules, so this is like assembling all of the tools that I'm going to need. So I'm going to have Pandas, you know, for the data frame, Numpys for all my numerical Python work, and then I have Matplotlib for all of my basic charts and graphs. Then I also have Seaborn if I want to get fancy, and I also have Sklearn, which is what I'm going to use eventually for the modeling, and then I have Scipy for any type of statistical analysis. So I have already loaded those, and I'm loading in this Pi reads that data, and that is because my data set is in the form of a SAV file, but you will probably get yours in CSV or Excel, and so instead of saying read underscore SSP like I do, you would simply say read underscore CSV or whatever format your data set is in. So here I'm loading in the data set, and I'm giving it the name. I'm using this function that is part of the Pandas module, read underscore SPSS. And so when I do load in the data set, I'm assigning it to the variable name df underscore FHS, and you could name it whatever you would like. I try to give it an informative name because sometimes I will save this as the original version of my data frame, and then I'll create another working data frame such that if I make any changes that I don't want to keep, I can go back to the original data frame. So now this is the data acquisition state. Now this is a very quick, short data acquisition state. There are times when this is going to be a much longer process because you may have to scrape the data set off of the internet, or you may have to get it from a pipeline, or you may have to get survey data from Excel, and then you have to do, you know, a whole host of things to be able to get it in form such that you can then load it into your notebook and use Python programming. But we'll start with the simple. There are lots of CSV files, simple files that you can use to get started. And so you would load that into your notebook. So that would be the first step. And now we want to look in line, make sure everything is as it says and as is expected. And so the first thing you usually do when you load your data set is to take a look at said data set, right? And so we use the .head method, right? And so if you have the name of your data frame, whatever it is, .head, with that, you can see the first 5 rows of your data frame. And so here we see our data frame. We can see all of the columns. Well, here it's truncated, but we'll print out an actual list of the columns. But this is just giving you an idea of the structure of our data frame. It is, you know, it looks like an Excel table. There are rows, and then there are columns, right? So we first have age, then we have LDL cholesterol, we have smoking, fasting blood sugar, HDL, systemic blood sugar, total, and so on and so on. And so now we have an idea of what is in the data frame. And so we see that we have 34 columns in all, 34 columns, meaning 34 features. And here we're looking only at 5 rows, but that's not the extent all that the data frame contains. If we want to know how large our data set is, this is where we would use, our data we would use the name of our data frame. So we use the .head method, and we see the first 5 rows of our data set along with a truncated version of the columns. And if we wanted to get the actual dimensions of our data set, that is where we would use the shape attribute. So I click here, that opens up a new cell, and I can type in here. So I want to get the dimensions on. I'm writing that as some kind of message to myself or my fellow data scientists should they use this notebook. And I use the name of the data frame, which is df-fhs for data frame Framingham Heart Study data set. And then I do dot shape, and that gives me the size of my data set. So the first number is going to tell you how many rows there are, 4,578 rows and 34 columns. And we knew there were 34 columns here from our dot head, but now we know that there are 4,500 rows in total. So that gives us an idea of the size of our data set. Now, if we want to know more, get more information about our data set, about these features, then we use the .info. And the .info, what that does is it gives you a printout of all of the column names along with a count of how many actual non-null values. So here it says that there are 4,578 non-null values in the age column. So that means there are none missing, right? And they are all of the float data type. But if we look at the LDL cholesterol, we see that it only has 4,511 non-null. So there are missing values here. Similarly with the smoking, there's some missing, but just about 3, so not a lot. And we can go down the list and we see all of the features, and we can see here that most of them are floats, with the exception of diabetic status and the 10-year update. So there are mainly floats in here, but there are still some categorical type variables, right? So the floats, these are the decimal point type data type numbers, and the categories are classifications. And so we see what a data set is made up. And so here it gives us a summary, and there are 9 categorical variables and 25 float or these numerical type variables in the data set. So now we have an idea of what our data set looks like. One of the other things that I always do with my data set, as far as getting a preliminary look at what is contained, is to get some basic descriptive statistics on the data set. And fortunately, Python has a very simple code for that. So for basic descriptive, that's where I would use the .describe method. So if I do .describe and I print that out, so here it's giving me the count, the mean or the average, the standard deviation, the minimum value, the 25th percentile, 50th percentile, the 75th percentile, as well as the maximum value for each of the columns. But you notice here that it's just 25 columns in this matrix for the .describe, right? And if we go back to our data set, when we did .info, we remember that 9 of the columns were categorical and 25 of them were numerical. And so when we applied the .describe, it only, I should say by default, it would only give the basic descriptives of the numerical values. And I like to transpose that. So if I do the .transpose on that, and it would just transpose that table. So now you can kind of compare the means of each of the features. It can give you an idea of whether there are some extraneous values, and I noticed that all of my values are in scientific notation. So let's repair that. So I ran this code here, pd.set underscore option, and the first parameter is the display format, and I'm telling Python that instead of the scientific notation with all of those zeros and the 10 to the power and all that, just give me a maximum of 3 numbers after the decimal point. So that's what this code does here. And so now if I can look at my table now, I can see that I get a better idea. The mean or the average age of the sample in data set is 40. Then the minimum is the youngest person is 19 and the oldest person is 83. And then if I look at the median, which is the 50th percentile, that is 41. So not too much skew going on there. The mean and the mode are the median are almost the same. But if we look at some of the other values, for example, LDL cholesterol, the mean here is 111, but well, we have a max of 281 and a min of 22. Yeah, so there's quite a range, and that's probably contributing to a larger standard deviation. But again, here the median is not too far from the mean. Sorry, but so just this gives you some kind of a very brief view of what's happening. So it may or may not allow you to see if there are any crazy values. But of course, you want to go beyond just this chart and do your due diligence as far as the distribution of these values are concerned. But so this would be the basic steps that you would perform when you load your data set in. You would first do the dot head to get the first 5 rows. You would do dot shape to get the dimensions of the data set. Then you would do dot info to see what the data types are for each of the variables. And here, we're predicting heart disease, and so we want that to, that would be the target variable. So we want to know what data type that is, and we're going to look more closely. But so you want to just kind of do those first, and then like I did with the dot describe to get an idea of the descriptive statistics. So that was our look at the data set, the preliminary look at it, as it were. So we have acquired our data set, and we have done a preliminary scan of the data set. We know the size of the data set, and we know what types of values are in there. So now we're going to do some filtering of the data set, right? This is where we're going to be looking for outliers and noise and any kind of extraneous type of values that should not be there. So let's move back to our notebook here, and we're going to go back to the top where I was. So we did our data acquisition steps, and now we're going to do our filtering. And so the first thing that we want to do with the filtering is when I did look at the data set, so if we go back to the first 5 rows, we notice that there's this PID number here, and when we did info, this PID is showing up as a float when it shouldn't be. It's just an ID number for the hospital kind of thing, or whatever system is used, and those types of numbers are usually of no value to our modeling activity, and so those are the invalid type of data that we want to get rid of. So I'm going to remove that from my data frame, and so I'm using the dot drop method, and here I put the column in question, and I let the function know that this column is, it is a column, so therefore it will be found in the x-axis, hence x is equal to y. And when I do that, I'm removing it from the data frame and reassigning that filtered data frame back to my original. Now I could create a working data frame here at this point, but I don't think I will ever want to get that PID back again. If I do need it, I can bring the data back in like I did originally. But once I've done that, and if I were to then do a look at the dimensions for my data frame now, I do dot shape again, you will notice that it has gone from 34 to 33 columns because I removed one. Now the next thing that you want to do is you want to look for missing values, right? This is important. Missing values can cause big problems for your analysis. So we want to find the missing values and we want to deal with the missing values. So we use the isNull method to find the missing values, and what that is going to do is going to look through the data frame, and wherever there's a value it's going to say true. Wherever there is a value, it's going to be false. That means it is not null. It's kind of a counter logic. And when there is a missing value, that's when it's going to say true. So that's what it looks like. So all these falses mean that there are values there, and so we would get that. But what we really want to know is the total of all of these missing values, and so that's where we do the isNull dot sum, right? And so I just comment that out in the meantime. And if I did that here, so that is going to tell me for each of the columns in my data set how many missing values. And we had kind of seen that the LDL had some issues before. Smoking only had 3 values missing, then total cholesterol 5, and diabetes, and so on. And so the extra code that I'm adding here is now going to take these numbers and return a percentage of, or a proportion of what is missing. So here we see that for the LDL cholesterol, that 1.46% of the values are missing. Similarly for HDL, 0.153%, and so on and so on. And so that's what that does. Now, when it comes to missing values, there are a number of ways that you can deal with the missing values. And they first depend on the quantity of missing, the proportion of missing. Now, normally if it's below 5 or even sometimes below 10, depending on the size of your data set, you can simply delete the rows that contain the missing values. But one thing you must pay particular attention to is when removing missing values, you do not want to create any unwanted bias in your data set. So for example, if we had more cholesterol values missing, say 10-20%, and we were to determine that a large proportion of those were women, if we deleted that, then we've introduced bias in our data set, right? And so we want to make sure when we are treating our missingness, we understand what type of missingness it is. And there are types to missingness, right? Because you can have missing, you can have different types of missing as far as these data frames are concerned. And so you have different ways of dealing with the missing values, because it will have different effects on your data set depending on what these missing values are correlated with. And so there are MNAR and M. Hopefully this should help bring it up to me if I see the type that I'm looking for, and I guess it was outlined here. Missing not at random is one type of value, and then you have missing completely at random, and then you have missing at random. So missing at random is probably the most benign of the type of missingness, so there's no correlation to the missingness. Then missing not at random, meaning that there is some pattern to the missingness, and then missing completely at random. So this you would have no consequences for deleting. The missing not at random, you don't want to delete that, you want to treat that. Missing at random, meaning that there is a relationship, some correlation with other variables, not necessarily the target variable. But we have such a low proportion of missing values that it may not be cause any issues as far as dealing with that is concerned. So what we have, I want to introduce you to this missing no module, which is one of my favorites because it helps give visualization to your missingness, right? And of course we don't have a lot of missingness, so there's not a lot to see. But see this column here, LDL cholesterol, and you see that that bar is not as high as the others. Similarly, the fasting blood sugar. So those are where they were missing. If there were more values missing, there would be more variation in terms of the height of the bar. You can also use the matrix, the dot matrix method from the missing though, and it would give you a matrix, and it would show you here LDL is missing values in these 4 places and so on. And this looks completely filled for the most part. When you have a data set with a lot of missing, you're going to see a lot of white spaces in there. And then of course you can do the heat map for missing values, and this will show you any type of the correlation between the missingness and others, and so here we see 0.3. Those are very low correlation, but total cholesterol of course is correlated with high cholesterol, because total cholesterol is a sum of low cholesterol plus so LDL plus HDL, so therefore definitely correlated. But just giving you some ideas, some tools with which you can play when you are doing your exploratory data analysis. So back to dealing with missing values. So we had 2 or 3 columns that had more than others missing, right? So most of them were below 0.3%, but there were some that were around 1 point something. And so what I'm doing here is I'm using the fill NA method. And what that does is it allows you to fill in the missing values with a defined value. And here we are using the average of that particular column to fill in for all of those. So we're taking the mean LDL cholesterol and we're filling that into the places where LDL cholesterol is missing, and then we're reassigning this new filled in column to our data set here. And we're doing the same thing with the fasting blood sugar. We're using fill NA, and here we're defining the mean of that column, and then we're filling that into the column, and then that is going to replace the column that is in the data set. So that's what's happening here. So if I ran that, we've now filled that in, and if I do my missing check again, so now we see LDL cholesterol, which was missing values when we did it up here, right? We saw it was missing here, and then the other was fasting blood sugar. And so now that we have done that fill NA method, we now see that LDL cholesterol as well as fasting blood sugar, they no longer are missing any values. And so for the rest of the columns, because the proportion of missingness is small, we usually use a threshold of less than 5%. I could have deleted these with not much of a consequence, but just to give you an example of how you would do that. And then once I've done that, now I can, as far as the other columns are concerned, I'm just going to drop the rows that have missing values. And that's what that's what the drop NA method does. When you apply drop NA method to your data set, it's going to look at each of the rows, and if there is any value missing in any of the columns for that row, it will simply remove that row. And so if we apply that now, and we did a check of my data frame, I don't know why I have all these extra commas here. That one I do need. If we applied that now, then we see we have dropped all the missing values, and there are no more missing values. All of the columns are completely filled and accounted for. And so now we've taken care of our missing values. Now when it comes to filtering, we look for missing values, we look for duplicates, and we look for outliers. So there is a very simple code that we use to look for duplicates. It's called .duplicated. And so we use that to check if there's, just like we do the check for missing numbers, we use .duplicated to check for if any of the rows are duplicated. Now, of course, by default, that's what it checks for. You can check for duplication as far as the columns are concerned, but with this data set, only 34 columns, very unlikely there will be duplications. You know, when I work with larger tables that have hundreds of columns, then for sure we want to make sure and check that none of those are repeated. So if we did the dot duplicated, it would return false if that row is completely unique. If there were any duplicated rows, then it would say true, and then when we applied the dot sum, then we would get a summation of the number of rows that did have that are duplicates. And if they were duplicates, then this would be the code that we would use to remove any duplication, right? So we would use the .drop_ duplicates, and if we don't put anything in the bracket, it'll just remove all of the duplicated rows. Now if we only want to measure or to take into account duplication in a particular column or a particular subset of the data frame, then we can define it here. So let's say we only want to look for duplication as far as, well, we got rid of the ID number, but let's say we wanted to see if there were any IDs that were duplicated in the data set. That's how we do it. So we would use the .drop_duplicate, and then we would put the PID, the name of the column, in there. But we do not have any duplicates in this data set, so we really don't need to. I just included this as an example for you. And so that's what we would do when you want to find any duplication in the data set. So another important part of the data filtering process is making sure that the formatting is correct and the data types are correct. Now, if we remember when we did the info method on our data frame, we saw that, oh, and I already ran the code, so it's showing up as a date time. But originally, if it's still saved here, when we did do that, the date time, this was showing up as a float. and so that is a time value, and so we need to do some data conversion here, and I don't see it, it's probably in the middle here somewhere. So this was showing up as a float, and it's not supposed to be a float, and these are some of the things that you do when you look at your data set. And so because it's not supposed to be a float, I ran this code here, the pd.toDateTime, and I used the date column to convert it to a Pandas datetime object here and reassign it back to the original column. And so when I ran the info now, this feature is showing up as it should, as a date time object. Just something to show. Now, moving on to the exploratory data analysis, right? This is where all the fun happens. This is where you get to get your hands dirty, like I say, and really get to understand this part of the process. Why I love this, because it's statistics, and I'm partial to statistics. So one of the first things you want to do is to look at the correlation between the features, between the columns. And so, because for some modeling activity, you don't want there to be any high correlation, but even if that, so you want to know what kinds of patterns there are, and if there are variables that are highly correlated, they might be measuring the same thing, and then you have to make a decision about which ones you want to get rid of and which ones you want to keep. And so if we apply the .core method, this is going to give us a Pearson correlation between each pair of variable, and this is what it looks like. But very rarely do we look at it in the raw numbers. We generally always put it inside of a heat map, because you know the colors, the pictures are much more cognitively light and easy to understand. And so what this is showing us here is that all of the light colored ones, maybe I move my head out of the way, all of the light colors, the lighter the color, the stronger the positive correlation. So of course all of the features are strongly correlated with themselves, hence these light colors going across the diagonal, right? So these are all ones. So fasting blood sugar is of course highly correlated with fasting blood sugar. So you want to look outside of the diagonal to see what the relationships are. Now, the lighter the color, the stronger the positive relationship. And then the darker color is for negative relationships. So 0 is around here, and then dark colors, I mean, the lowest it gets, I am thinking it's about minus 0.3. Gosh, now I can't do that over. I was startled by my husband. I feel like I should reduce the screen somewhat. Just zoom out a little bit for, at least for this correlation, this heat map here, because we can't really see the whole thing in that view. So here we go. So now we can get a better idea, right? So we have all of the features both in the X and the Y axis, and all of the light colors are where the strong positive correlations are, and then the darker colors indicate the negative correlations. So HDL cholesterol is negatively correlated with almost everything. It's negatively correlated with fasting blood sugar. It's negatively correlated with BMI. It's negatively correlated with, so there are 2 rows for fasting blood sugar here. So what, this is, of course, what is this saying? The features that are strongly correlated with the outcome, which is heart disease. Now, it's not included here in this correlation matrix because it is a categorical variable, and this is a Pearson correlation, which is measuring linear correlation between continuous variables. So that's what happens. Sex, gender is included because it's just 1 and 2, so that's okay. And so what we're seeing here are correlations, linear correlations between the floats, those numerical values that are for the most part continuous. And so this is how we would kind of get some idea of what's happening. And so HDL cholesterol is associated, is known as the healthy cholesterol. And so that would explain why, to some extent, it's negatively correlated with all of the others features that are pointers towards heart disease or ill health or not as healthy kind of thing. So HDL is a marker of good health. And so we would see that. Oh, we do have the heart disease. This is the target here. And yeah, so heart disease. Now, if we notice here, now this is a binary feature. We're going to delve into that whole feature very soon. But it is binary. So it is showing not too much happening by way of correlation with any of the other features. But again, this is only measuring linear correlation, so you have to be careful. Not because it's not linear correlated doesn't mean that there is no relationship. It just means that the relationship is not linear, and there are other types of relationships. So we look at, of course, total cholesterol is highly correlated with LDL cholesterol because total cholesterol is the sum of HDL cholesterol and LDL cholesterol. So not much information there. Fasting blood sugar is highly correlated. So I'm trying to see, what insights we can get from this chart, this heat map necessarily. There's not much, but one thing I can point out is that there are these interaction features here, which are created as a combination of other features, right? So we have glucose with blood pressure, and diabetes with HDL, and diabetes with systolic blood pressure, and so on. So these are interaction variables. And we notice that, the interaction variables are, there might be something going on here as a pattern. It's the lighter colors, indicating a stronger correlation between the variables as opposed to the left hand side, which is tending to be darker. So we see something happening here. So total cholesterol is negatively correlated to some extent with the diabetes HDL and the diabetes SBC, or systolic blood pressure variable. But yeah, so just to kind of give you an idea of how to interpret some of these findings. Nothing stands out in particular. So what I would be interested in mostly here at this time would be the target variable, but again, not much by way of linear correlation. So that's that. If we can generate a table of the correlation with each of the variable and just the target. And so what I did here, I used the .core method on the data frame, and then I used the square brackets to select only the column with the column for the outcome variable, and I then got the absolute values because some of the correlations were negative, and then I sorted. So doing that now, I can see, and maybe if I sorted and I said ascending equals false in this case, then we would get the reverse order. And so we see that as far as the linear correlation is concerned, age is the strongest correlation with the outcome or heart disease. And then there is a fasting blood sugar, systolic blood pressure, interaction variable, then there's glucose and the blood pressure interaction variable. So we get some idea of the relationship. And here I generated a graphical representation of that. Actually, I thought it was just 4, but just another code to look at the heat map. But we can do the SNS dot heat map here and see how that shows up for us as far as just that column is concerned. Yes, so I did a heat map of the correlation matrix and I selected only the column for the target, and that's what that looks like. I did not sort it, so the target is in the middle kind of thing. But again, age is at the top with LDL, cholesterol, and smoking. Well, smoking, these are negative. So this is not well, that's not that code, but it's way you can generate. You can look at just the variable in the outcome. This is just another correlation matrix heat map using a different scale for the coloring, and so it allows you maybe to see, and it also includes the anode equals true so that you can get the actual values for the correlation coefficient. All right, and so that is how we would do that. So let's look at some, see if we can find some outliers. So we're looking now for outliers, and because we know that our data set is made up of 2 or 3 types of data types. Now we have numerical values as floats, and we have our categorical values as objects, and then we have the date time. So we can create a subset of the data frame that contains only the floats or only the numerical values using the .select_d types. And so here I'm doing that, and then I put inside of that function the data type that I want included into my new subset. And so if I did an info on that, I would see that I now have this new subset, 23 columns, and they are all floats. So now that we have that, we can use that to generate some plots to look for our outliers. And so that's what this code is doing here. We are going to generate a histogram from that this new data subset that we have here, and I'm going to get them as subplots, and we'll see what that looks like. So we have our histogram here, and so in checking for outliers, I noticed that there was an additional column that was an ID column, and at least it was an ID type column, which is interesting, but I went ahead and I removed that column from the data frame, and then I was able to get a better numerical column. So you see now it's no longer containing the PID or the ID type. And so here we have the numerical column FSH_num, and now I also I was curious about these fasting blood sugar, and then fasting blood sugar _1, and then fasting blood sugar _BG. Yeah, so I was wondering, are these all the same? So I did a correlation between the fasting _BG1 and the fast underscore BG underscore 1, and sure enough it is 100% correlated. So I did remove one of those, and just to confirm the shape of the data frame, the subset. And so now I'm going to use this subset of the data frame to generate a series of histograms. So for each feature, I'm going to generate a histogram. It's going to have bins of 30. There will be no grid, and the entire data, the entire visualization will be a 30 by 20, but there will be 3 rows and 7 columns, so we can get an idea of how these values are distributed. So here we have age and LDL and HDL, and you know, these are the ones that are normally distributed, at least to some extent. It's not perfectly normal. But then if we look at smoking and fasting blood sugar and heart disease, of course the target, significant imbalance here, gender, these are all actual categorical variables that are labeled with numerical values. And so that is something that you want to pay attention to. Right now, the interesting thing is, for the exploratory data analysis, we need to treat them as categorical. But then when we go to build our model, we need to treat them, we need to do some way, masking them such that they are represented by numbers, because the algorithms, the machine learning algorithms, do not recognize categories. But so we generated this series of histograms, so it gives us a very good idea of how the values are distributed in our data frame. As far as the outliers are concerned, so there's skewness here, definite skewness going on here with this variable, very much skewness going on here. For total cholesterol, the mean is 200. Somebody is out here in the 650 plus category. So yeah, so these are all skewed to some extent, but where I think there's an outlier, it would more likely be with this total cholesterol. If there are even though the range is wide, but there are values, you know, going all the way between, then it's not an outlier necessarily. That's just the distribution of the variable. But with the HDL cholesterol, now that one is an interesting thing to me, and so I would go ahead and either do a separate histogram for that. But here I have the code for the for generating box plots for each of those distributions. So let's see what they look like, and we can then get a better idea for each variable. And again, that's for those that are labeled floats, i.e. continuous, or numerical, I should say. So these are interesting. These are the box plots for each of the variables. So there's age and LDL, there's smoking, of course, that's a binary. Fasting blood sugar, definitely categorical. And then we have I think I see they probably used the continuous variable and created another variable, a categorical variable from that. So yeah, so the one that we were saying had a lot of skew, that was total cholesterol. So let me see what the box plot for that looks like. So that, yeah, that's classic outlier going on over there. This is the heart disease. So it's a binary. And what else are we looking at? Anybody looking out of the ordinary kind of thing? But that's how you would look at the distribution to see if there are any outliers, and then subsequently deal with that. So if you wanted to get a box plot where all of the columns are on the same plot, that's easy. You don't need the for loop per se. You would just do the data frame dot box plot, and that would give you a box plot. The challenge with that is the variables are on different scales, so the ones that are on the larger scale are going to dominate and you can't really see anything. If your variables are on the same scale, then that should be enough, but of course usually they aren't. Alternatively, there's the facet grid. That's another way of generating these subplots, and so that's SNS. You would use your data frame, and what that does, it gives you a nice bivariate analysis. So here I'm generating scatter plots of pairs of variable, right? So I want to see fasting blood sugar against cholesterol. But with the facet grid, what it's going to do, it is you can define a column, so it's going to separate each plot by the categories of whatever column you specify here, and then you can include a hue so that when you generate the scatter plots, you have the X and the Y as defined here, and then for each category in the age group, so we have 26 to 40 here, 41 to 55, 56 to 70, less than 25, more than 70. So you have each chart representing one of these. And then you also have the hue to represent the distribution of heart disease. So, and this can be very interesting. Now, mind you, this is a small data set, so some of the categories are sparse, so less than 25 and over 70. Not a lot. But as you can see, even though there's not a lot of people over 70, the proportion of them that did have heart disease, which is the orange markers, is much higher for any other category. And I mean, that makes sense. They're the older ones. And similarly, by contrast, for the youngest group, there's a very low proportion of them that would have had some type of cardiovascular illness. And yeah, so that can give you, and you can change these out into whatever feature you want to look at, keeping the heart disease because that's our target. And yeah, and just kind of change up the how you want this broken down. So you need a categorical variable here in the column section, and then you need two numerical or continuous variables when you actually generate the scatter plot. But that's one of the nice things about this facet grid. And here finally, if you want to see box plots of the variables with doing a bivariate type of analysis again, so you're looking at the age groups like we did here, and so you're generating a box plot for the total cholesterol measures for each of those age grouping, right? And so we see for the youngest, they have the widest range. Oh wow. And this is where our outlier is. So see why it's important to really dig into your data, because here you have someone in the youngest age group having the highest total cholesterol value. Now again, we have to go further to that, because is that total cholesterol high because of the HDL or the LDL? Now that is important to know, because HDL is a healthy cholesterol, whereas LDL is not so much. So we want to see what is the contribution of his total cholesterol. So I'm going to switch this out. Instead of the HDL, I'm going to have, instead of total cholesterol, I'm going to use HDL and see what happens. Very interesting, because now instead of this person in that young age group having the high cholesterol, is someone else is standing out here. So what that is telling me is that this person who had that high cholesterol, it was not HDL. So, you know, that is a very something that should be noted. And now this person here, an outlier, but it's good outlier because this is HDL. It's a healthy cholesterol. But you know, we're not dealing with individuals here. We're looking at patterns in the entire data set. But these are just some of the things you, as the scientist, the data scientist, you have to have that understanding of your data set. So we looked at all of the numerical values. Now we're going to look at our categorical variables, right? We had subsetted the data set, took out all of the numericals. We're going to do the same thing. And so now instead of including the floats, we are excluding the floats. And that is going to give us all our categorical values, including our date. And I think I may just drop that from my categorical subset, just because the type of analysis that we're doing is not suitable for date type of analysis. It's a whole different type. So we're going to drop the date from that category. So we're using our drop method, and we'll identify the column, and I'm going to use that here, and then I'm going to stipulate the axis as being that, and then I want to make sure that it did what I intended to do, and I'm going to check it again. Very good. So now our data is gone. We have 9 columns, and so now we can, with the categoricals, we can't do histograms, we cannot do box plots. Those are for continuous variables. Here we do bar charts, and we do single bar charts. We can do stack bar charts, column bar charts. It's all about the bar charts in this when it comes to the categorical variables. But mind you, Python has a variety of categorical plots specifically for categorical variables. But one of the things I like to do for the categorical variables is the n unique. And so what that does, it tells you how many unique categories there are in each of the variables. Now, when I do this, I also sort it, and I see something very, very interesting here. So now smoking, 2 categories, that's fine. Sex, 2 categories. Diabetic status, 2 categories. Heart disease, 2 categories. So all of these, let me see, missing. So up until here, I think those are true categorical variables, and the others might be mislabeled. Because if you have fasting blood sugar with 129, and then, there's another date column in here, right? And BMI with 3,000 categories. Yes, those are definitely giving continuous or not categorical variables. Those large number of categories are reminiscent of the continuous variables. So I went to transform that. So here's what I'm doing with this, right? I'm looking for the number of unique categories in the variables, and I'm creating a whole new data frame with that, and I'm going to now rename the columns. And then what I'm going to do is I'm going to change those to the integers that they should be, as opposed to keeping them as floats. Yeah, so I went ahead and did a count. Then I I did a conversion, a data type conversion, because I wanted to be able to sort the number of categories and separate those with a large number of categories from those with less than 10 categories, because I believe those are the true categorical variables. So that's what I'm doing here. I'm creating a set of features that are actual categorical variables. And so this is what my new subset of categorical variables look like. Those were the ones that were originally labeled as numerical. And then we had the original categorical variables. And so I wanted to generate a plot of those original categorical variables. And I think I may have not included the main variable in here. So let's go ahead and add that to my data frame. So that dhcat underscore, we're going to get chd back in there, and that is going to come from, we can get it from the main data frame, right? Because when we separated out our categorical variables, that got rid of the CHD. So we're going to put that back as that cat column. And did we not define the categorical variable originally here? This was my categorical variable here, and this is what I'm using, like the name of my data set. I've switched the abbreviations. FHCAT, and this one should be what is the original name of my data set, and then here we go. Okay, so now we've added the CHD back there. So now we can see these plots, these categorical plots with respect to the target variable. So here we have diabetic status, for example, and it's showing you of the non-diabetics. Of course, majority of them, they had no heart disease, right? Now, mind you, there is such significant imbalance in the target that it doesn't even make sense to look at these, because if we were to look at the distribution in the target variable, we would see the measure of imbalance. So the target variable is the CHD, and if we did look at that, if we did our original, or any one of them, because they all now contain the outcome variable, so we could do simple value counts, and that would give us an idea of how, what the distribution is like, but we already know that it's significantly imbalanced. And yeah, so we see it's 4,400, no heart disease, 127. If we wanted to get that as a proportion, then we would say normalize equals true in this case, and that would give us, so yeah, 0.28 of the population of the sample actually had the heart disease. So significant imbalance. So therefore, if we want to model this data, we would have to treat that imbalance in some way with smoothing or some other technique to kind of get that imbalance to not be so severe. So let's see how we're going to do that. I do not have. Okay. Right, so we have our k-fold cross-validation, and we're going to do 10 splits, and then we're going to see what the mean and the standard deviation for each of these versions are, and it's 78.8, less than when we just did regular cross logistic regression. Now here I'm going to do some shuffle split. I'm not sure why I have this code for the dimensions of the model is the data set is concerned. So now again we are going to do a shuffle split instead of the k folds this time, and I did actually run that and did not get anything different as far as these models are concerned. Here I'm using the scoring method as accuracy as opposed to the default, and so when I ran that I got an even smaller. But we also did the log loss, negative log loss as the scoring method for the cross validation, and we looked at the mean of negative log loss as well, the log, and then the standard deviation of that. So we see all of our models here. Then finally looking for the AUC of the logistic regression, and here we are doing so we're doing the ROC AUC as the scoring method, and we'll get an accuracy of 85% or so. So yeah, that's an improvement. So we want to look at the confusion matrix and the classification report for our model. So I went ahead and did that, and I did not include, I should include the values. So I added this formula just to get instead of getting the values in the scientific notation, I'm actually getting percentages. So I'm dividing the values in each of the quadrants by the total, and then I'm representing that as a percentages. So we can see that, for example, the true negatives here for 39% are true negatives, and then 40.63 are the true positives, and then we have 11.58 as the false positive, and then 8.77 as the false negative. So that's how you would generate that, right? So we had the model, we got the prediction, we used the predictions to get the confusion matrix, and then we put that confusion matrix into a heat map. Alternatively, we could do a classification report, so it would give the precision and the recall and the F1 score and support. All of these can give some way to estimate the performance of the model. And for example, if we went in and we optimized the model in any way, and then we generated a classification report again, we could see where what improvements were made, how did it perform differently. One last thing I want to show, is how we can get an estimate of the feature importance. So we have a list of features as is found in the column, the original data frame that we're using. I do not need this anymore. And then we can also get a list of the coefficients from our model. So these coefficients actually match these feature names. And so we can, in order to bring that into one object, we first would unravel the coefficients, the name of the coefficients, into actually the values of the coefficients here from this array into this list, and then we can combine that in a dictionary that we then convert to a data frame, and this is what it looks like. And if we wanted, we could actually do a sort of the values, and we would sort by the coefficients, and that's uppercase C here, and then we get another print. That's not what I want to do. It won't let me copy and paste that. Hello. Right, and so there we have it. Did it sort? I don't think so, because I did not reassign it back to the table. So it sorted and then it went back to whatever it was. So now I want that to be the new data frame, and if we generate that, I'm not sure why my notebook is no longer responding. There we go. So that was not unraveling because I already made changes to it as far as the coefficients are concerned, and here we are. So we have sorting of the data frame, the coefficients. Now I did not make the values absolute. That's something else that I can do, but before doing that, I'm going to generate a plot. So I'm going to take this data from that data frame, and I'm going to plot so we can see what these features look like as far as which ones are important. So here we see that age is the most important with respect to increasing the likelihood that you would have heart disease, because this is negatively correlated with the outcome, and so that means you have a greater chance of getting the disease, which is labeled as the one, than someone younger. And similarly with the LDL, smoking, all of these are negatively associated with the outcome, whereas we see that this combination of coefficients is the strongest predictor of an outcome of heart disease, followed by fasting blood glucose and HDL. So these are all the interaction variables, and now they are very good to include in a model, but when it comes to actually risk factors that you can make some changes to lifestyle modifications, then these are the ones that you would focus on. This would be good for modeling and being able to screen to find out someone's risk of heart disease. But then when you want to give them some concrete things that they can do as far as their lifestyle is concerned, then they would definitely, you know, focus on these features here. So we looked at the modeling factor here, and we did quite a lot. So we did smote because of the imbalance here, and when we smote, this was how we got that imbalance. Then we used the standard scaler to scale our X variables, and then we generated a bunch of models. We did the logistic regression with k-fold, logistic regression with shuffle split. We did a logistic regression where we looked at either using accuracy or negative log loss or the ROC AUC, and we generated this lovely confusion matrix here, and then finally we got a feature importance chart in terms of how the variables stack up with respect to the outcome. In another video I'll do a cat boost, but I think this video is long enough now.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.